when it comes to phase shifts of sinusoids, there can be some ambiguity for how you interpret what exactly the phase shift means graphically in relation to both the equation and the graph. And you might have actually noticed this yourself as we've gone through the course. And so in this video, I want to clear up any confusion you might have here. And actually, in the process, the ideas we're going to talk about, it's really not just about phase shifts of sinusoids. You can apply this idea to any horizontal or vertical translation for any graph, not just a periodic function, any graph. You can think about translations this way. Okay, and so to go through this discussion, I want to come back to an example problem that we looked at in the textbook related to alternating current coming through a wall outlet. Okay, so what we saw was that the voltage coming out of a typical wall outlet, it's not a constant, it's a function of time, right? It's alternating current. The voltage you could write as 163 sine omega t, where t is the time and omega is the angular velocity. Okay, and so we were told this and then asked the question of if the electrical generators at the power plant are required to rotate, very precisely at 60 cycles per second, then what must the omega be? That would be the angular frequency. Well, okay, if the electrical generators are rotating at 60 cycles per second, then that means the electric current coming through, it's, if it's, we know it's sinusoidal, so it's going to be, the sinusoid is going to be one cycle, or no, it would be 60 cycles every second. So one cycle would be a 60th of a second. One cycle every 60th of a second. That must be the case, right? Because that's the electrical generators are rotating at 60 cycles per second. That's going to be the frequency of the sinusoid, because they told us it was a sinusoid. Okay, and that makes sense because the electrical generators are rotating in a circle. So, and we know how the circle is related to the sinusoid. So, okay, but we know that if we want to get the angular frequency, all we think about is the circle that corresponds to, that's tied to this sinusoid. When you go through one cycle, you're going through 2 pi radians. The angular frequency is not how many cycles per second or per horizontal axis unit. It's how many of the radians you've gone around the corresponding circle. So omega then is, you haven't gone one cycle every 60th of a second. You've gone 2 pi radians every 60th of a second, which is 120 pi. Okay, so there we go. The voltage is 163 sine of 120 pi t. Okay, so then the next thing we were asked is if we had a voltage given by, and then cosine given by this, then what must the psi be to where this is equal to this? Like if you have a certain value of psi, then this just simplifies to 163 sine of omega t. Okay, and so the ambiguity comes in the sense that, so I'm not an electrical engineer, and I'm not sure what the official terminology for sinusoids is, but when you talk about a phase shift of a sinusoid or a phase shift of any kind of periodic function, I'm not sure if they're officially saying, like, is this the official term for a phase shift, or is so you could also write it like this. You could say 163 cosine, you could factor out the omega, and you get this. Okay, is this the phase shift, right? You could make this another variable, alpha. So is alpha more of what you'd officially say is the phase shift? And I'm not sure what math defines or to be the official terminology. Maybe it's like any particular engineering or science field might have their own way of looking at what phase shift, the technical definition for phase shift is. But that's the ambiguity, though, that I'm talking about is, you're looking at, is this a phase shift or is this the phase shift? And, just from a graphical standpoint, to me, it's this second formula here is how you would interpret what the phase shift is. And so, but why am I saying that? Well, okay. Here is 163 cosine omega t with omega 120 pi. So that's this here without any, with this psi equal to 0. Okay. So now, to me, when I think about a phase shift of any periodic function, not just a sinusoid, and furthermore, not even just phase shifts of something periodic, but an actual, any kind of translation, vertical or horizontal, of any graph, of any function or relation. The way I think about it is you have the graph has had its shape changed to the shape it's going to be in, its final shape. And then that final shape has been shifted by a certain amount to a certain position in the XY plane. That's the way I think about it, right? Because like what's going through the wires is this sinusoid here. It has a certain frequency, has a certain amplitude, right? So here it is. This is the nature of the voltage going through the wires. And so now if you're going to ask me what's the phase shift, well, then to me, you're asking me, well, how much has this sinusoid shown on the screen here, how much has that been shifted? That's my sense for what the phase shift is. And if you looking at the equation from this perspective, that's exactly what this is telling you. However, when you put it in this form here, that's not what this is telling you. What this is, so what is this here? This is, so it's, you imagine you could start with 163 cosine of t. There's no omega applied, so it's going to have the full period of 2 pi. But you could still apply you could scale it up to have the big amplitude, but the period isn't changed. It has period 2 pi. Okay, then you shift it horizontally by a certain amount, and then when you apply the omega, it shrinks everything down, but it also shrinks that shifted point down by, like, so when you multiply by omega, that means you're multiplying every x value by the reciprocal of omega, right? And so when you do that, you multiply every x value, but you also multiply the x value of the shifted position, right? And so to me, that's more confusing, because you're saying that if you look at this as the phase shift, well, then, but once you apply the omega, this isn't the actual amount the graph is shifted. So now, again, whenever you're in engineering or you're in a certain field, they might actually call this the phase shift, and if that's how they define it, that's fine. But still, it's good for you to understand the intuition behind graphically the actual true sinusoid on the graph. What's its actual shift? Okay, so we can, if we want to answer this question of how much does this psi need to be in order to where this is equal to 163 sine omega t, where this is the omega, the most intuitive way of looking at it to me is we're trying to find what is this distance right here. This amount of time, how much is that time? That's what we want to shift this sinusoid. Then we'll have a sine graph. Okay, and so, but that amount is the psi over omega. Okay, so, but what is this amount? Well, okay, we know that one cycle is a 60th of a second. But we can see, though, that this is a quarter of a cycle. So what is 1/4 of a 60th? That's 1 over 240. So psi over omega is equal to 1 over 240. Well, we have omega, we can just solve for psi. So psi over omega is 1 over 240. So psi is equal to, cross multiplying by omega, 120 pi over 240 pi over 2. So 163 cosine of 120 pi t minus pi over 2 is equal to 163 sine of this omega 120 pi t. Now, again, so what is this pi over 2, though? What exactly does that mean? The idea is, before this graph was stretched horizontally, it was shrunk horizontally down to this small frequency, or no, small period, high frequency. It's like you shifted it before you did that stretching. You shifted it to pi over 2. Then you applied the horizontal scaling by multiplying the t value by omega. Well, so that, what does that do? That multiplies every single t value, or yeah, I think I might have been saying x value before, t value by the reciprocal of omega, but it also applies that to the shifted position. So it kind of reshifts it when you do that, which is what I don't like about looking at the phase shift from that perspective. So that's why if we took, okay, so pi over 2 times the reciprocal of omega, what do you get? There you go. That's the actual shifted amount. This is psi over omega. Okay, and it's this exact same logic when you think about vertical shifts of not just sinusoids, but of any graph, of any kind of function or relation. To me, if you're trying to understand exactly what's physically happening to the graph, you want to look at it from the perspective of the graph has already been reshaped, resized, flipped, and everything. And so now that's the graph. That's the graph you're dealing with. Okay, but how much has that graph been shifted off from the origin? And you can interpret that from the algebraic equation standpoint by always you factor out you have a coefficient of 1 in front of the independent variable. You have everything factored out to where you can see the coefficient 1 in front of the independent variable, and that's being added or subtracted from something. That's going to show you the true phase shift. Now with flipping, it gets kind of confusing because you could potentially you could factor out a minus, or you could leave a minus in front, a minus 1 in front of the independent variable, and so that there's some ambiguity there, and I've talked about that in other videos. But I would say a good common practice is to just have a positive 1, factor out negatives, everything, have a positive 1 in front of the independent variable, and that's being added or subtracted to something, and that's the phase shift. And then what's on the outside here tells you the amount of scaling, the amount of, or if it's been flipped, right? And so again, I would say put any transformations that have been applied to about the y-axis, put them into this form. About the x-axis, put them into this form. And this applies to any, periodic functions, non-periodic functions, whatever. Just to give you an example, let's say that for some reason this was shifted up 25 to about here. I don't know why the current would do that, but let's hypothetically. So that's okay. That was the cosine curve with psi 0 plus 25. Okay. Well, you can, so like the v of t is the y. You could write this as y, but to put it into the form where you can see clearly see the shifting and the scaling, you would subtract 25 from both sides, and then you could divide both sides by 163. So let's see. Okay, so there you go. There's that form where you can clearly see the transformations applied about the dependent variable axis. So it's been shifted up 25 and then scaled by the reciprocal of this about the y-axis by 163. Right? It's the exact same form. It's the exact same form as this. You factor out what you need to factor out to get a coefficient of 1 in front of the variable. So you can see what the phase shift is, and of the transformed graph, and you can see the actual scaling about that axis. And if you find this confusing, go through. I touch on these topics every now and then as we go through the entire chapter on the graphs of the sinusoids and tangent and cotangent, cosecant, secant. Also talk about this in algebra. So I'll post a link to a video in the description that gives a good summary of the different nuances of transformations of graphs that we talked about in algebra. I think this is really good, helpful to understand these concepts. So take a look at that video as well.